Hello students, welcome to Joint Chemistry. So today's video is about coordination compound part 2. So I already uploaded the part 1 video. So if you have not watched that video, please go and watch it. Okay. So in this video, we will talk about the calculation of the metal charge and also the IUPAC naming of the coordination compound. Now before calculating of the metal charge, let's talk about some statements or informations. For neutral complexes, the charge of the central atom, the charge of the central atom plus the charge of the all ligands is equals to 0. So what is neutral complex? Some complex which does not contain any charge. Okay, those are known as neutral complex. For example, this. Now this is a complex, as you can see, is a platinum and 5 ammonia, 1 chlorine into the coordination sphere, and outside of this coordination sphere, which is ionization sphere, contains 3 chlorine atom, right? So what is coordination sphere, what is ionization sphere? I already told you in the previous video, so you should go and watch that video. Okay, now this is a neutral complex. So for this neutral complex, the charge of this metal plus all of this ligand, the plus all charge all of these ligands is equal to 0. Okay, so the charge of this metal plus charge of all of these ligands is equals to 0. Now for the complex ion, the charge of the metal plus the charge of all ligand in coordination sphere is equals to the charge of the complex ion. Okay, for example, this. As we can see, this is a complex ion which contains a 3 positive charge, right? Now in this case, the charge of this metal and the charge of these all mm, ligands will equals to the plus 3, that is the charge of this complex ion. So this is the statement. So for complex ion, the charge of the metal plus the charge of the all ligands in coordination sphere. So this is the coordination sphere. In this coordination sphere, these are the all ligands. So charge of these all ligands is equals to the plus 3. So charge of the metal plus charge of these all ligands is equals to the plus 3. Okay. Now for the neutral ligands contribute 0 charge or no charge. Okay, any neutral ligands so will contribute 0 charge or no charge. Okay, and for anionic ligand it contributes -1 charge, and for positive ligands which contribute +1 charge. Okay, now for example, this is a complex where platinum, 5 ammonia and chlorine, and outside of this complex is 3 chlorine. Outside of this coordination sphere is 3 chlorine. Now here I mentioned their individual charges. Okay, so we have to calculate the charge of the platinum, that's why I mentioned X here. Now for ammonia it is NH3. It is a neutral ligand, right? So it will contribute 0 charge. Now in this coordination sphere there is a chlorine ligand is there, which is a ionic ligand, so it will contribute -1. And outside of this coordination sphere, in the ionization sphere, as you can see, the 3 chlorine ligands is there, so each of them will contribute -1 charge, right? So now in the polar solvent, what will happen? In the polar solvent, they will break, and this complex will produce 3 chlorine at chlorine minus, right? 3 chlorine minus, and for these consequences there will be a 3 positive charge, right? So this is the way it will break. Now this is a complex ion. So for this, let's say the charge of this metal is X plus every ammonia contributes 0 charge, so therefore 5 into 0, right? Because total there are 5 ammonia, so each ammonia will contribute 0, so total charge contributed by the 5 ammonia ligands will be 5 into 0 minus 1. Why? Because there is a 1 chlorine ligand is there, so which contribute -1 charge, so there will be a -1 equal to +3. Why? Because this complex ion contribute +3 charge, right? So therefore it will be equal to the +3 according to the second rule or second statement. For complex ion, this is the complex ion, as you can see, the charge of this metal plus the charge of the all ligand in coordination sphere is equal to the charge of this complex ion. So this is the charge of this complex ion plus 3. So all summation of these all charges is equal to the plus 3, right? So now x 5 into 0 is 0, minus 1 is equal to plus 3. So if we change the side, we will get x is equal to plus 3 plus 1 is equal to plus 4, right? So the charge of this platinum is 4. So this is the Roman letter. So actually, you know what? This is not the correct way to write Roman letter. The correct way is this. Okay, so this is not the correct way. We should not write these lines up and down. Only this, only this IV. Okay, this is means 4. So the charge of this metal is 4, right? So we calculate the charge of the metal. Now let's calculate the another one. This is a new neutral complex which a nickel and carbonyl. There is a 4 carbonyl ligands is there and the 1 nickel is there. So let's say the charge of this nickel is X. So X plus, now this is carbonyl which is a neutral ligand, right? So it will contribute 0 charges. As I already told you that neutral ligand contributes 0 charge or no charge. So this carbonyl will contribute 0 charge. So each of these carbonyl will contribute 0 charge. So overall there are 4 carbon, so 4 into 0 is equal to, as you can see, it contribute nothing, right? There are no charge on this complex, so this is a neutral complex. So neutral complex, for this neutral complex, the charge of the metal plus the charge of the all ligands is equals to 0. Now x 4 into 0 means 0 is equal to 0, right? So x is equal to 0. For this complex, nickel contribute 0 charges, or okay, so there is no charge on the nickel, so it is 0. Okay, so this is the way we can calculate the metal charge. So let's do some other examples. Now this is a complex which is a copper and tetra ammonia complex containing +2 charge, right? So this is a complex ion. So for complex ion, the charge of the metal, which let's say X, plus it is a neutral ligand, as you can see, because it is an NH3, so it will contribute 0 charge. So total is, there are 4 ammonia, so it will be 4 into 0 is equal to the charge of the complex ion, which is +2. So x plus 4 into 0 means 0 is equal to +2. So the x is equal to +2, right? So the charge of this copper is 2. So we will write this way in the Roman letter 2, I and I, right? Now for this complex, it is there is a K4 in the bracket FeCN whole 6, right? Now this is a neutral complex, so we can do in a two-way. Okay, we can do this in a two-way. We can consider it is as a neutral complex and calculate the charge of the Fe like this way. Now as you can see, this is a potassium, right? Now the potassium contribute -1 charge, sorry, +1 charge, sorry, it is a metal, so it will contribute +1 charge, right? So it will contribute +1 charge. So each of these potassium contribute +1 charge. So if the total there are 4 potassium, so it will be 4 into +1, right? Now Fe, for Fe we have to calculate it. So let's say it is X, and this is a cyanide which is an anionic ligand. It will for anionic ligand it contributes -1 charge. So there are total 6 anionic ligands, 6 cyanides, so there will be 6 into -1 is equal to 0, because there are no charge outside of this complex, because this is a neutral complex. For this we can say 4 into +1 is equal to +4, right? Or +4 plus x into -6. Why? Because they are -1. So if we multiply 6 with -1, we will get -6 is equal to 0. So x -6 plus 4 is equal to 0, right? Or x minus 2, because if we do this math, minus 6 plus 4 we'll get minus 2 is equal to 0, right? So or x is equal to plus 2 by changes the side, right? There is a minus 2, so if we change the side it will get plus 2. So the charge of this Fe is 2, right? So this is the way we can calculate the metal charge. Now let's do another example. Now this is again nickel carbonyl, so which I already have done. So again I'm doing is, so let's say it is x. So x plus, now there are 4 carbonyl ligands is there which contribute 0 charge. So 4 into 0 is equal to, there are no charge outside of this complex, so it will be 0. So x plus 0 is equal to 0, so x is equal to 0, right? Okay, now for this complex, this is K3 chromium and this is C2O4 whole 3. Now what is C2O4? C2O4 is the oxalate. Now what is oxalate? The structure of this oxalate is like this. Okay, so this is the structure of this oxalate. Okay, in the IUPAC naming it is known as oxalato. Okay, I already told you the names of so many ligands in the previous video, so you should go and watch that video. Okay, now for this complex, let's say the charge of this chromium is x. Now there are 3 potassium is there, each of them contribute plus 1 charge, so there will be 3 into plus 1 plus, this is their x plus, now each of these C2O4, there are 3 C2O4, each of these C2O4 contributes 2 minus 1. As we can see there in this structure of the oxalato or oxalate, as you can see there are 2 minus charge each of them, so each of them contributes 2 minus charge, so there are total 3, so it will be 3 into minus 2. Why? Because each of them contributes 2 minus charge, right? So is equal to 0. Why? Because there are no charge outside of this complex. So or 3 into plus 1 is equal to plus 3 plus x minus 3 into 6, sorry, 3 into 2 is equal to 6, so it is minus 6 because there is a minus 2, right, is equal to 0. Or x minus 6 plus 3 is equal to 0. So if we do this math, we will get x minus 3, because this is a minus 6 plus 3, so you will get minus 3 is equal to 0. Or we can get it x is equal to plus 3, right? So the charge of this chromium is 3. So by this way we can calculate all of the charges, right? All the charges of metal. So this way we can calculate all the charges of metal. Okay, now let's do IUPAC nomenclature. Now as you can see, this is a complex which is K3FeCN whole 6. Now the name of this complex is potassium, then there is a space hexacyanidoferrate 3. Okay, so how can we write this name? How can we write this name? Before we write this name, we should know some rules. Okay, the first one is, for coordination compounds that are ionic, it means there are some coordination compounds which are ionic. The cation is named first, followed by the anion. Now how do you know which one is ionic and which one is non-ionic? Now for some complexes which produced ions in polar solvent, for example this complex in polar solvent, it produced FeCN whole 6 minus 3 plus 3 potassium plus. So as we can see, in the polar solvent it breaks into this ion, it produces these ions, where this is a complex ion FeCN whole 6 minus 3, and this there are 3 potassium charge, right? In this case this potassium is the cation, so this part is the cationic part, and this total complex ion is a negative part. Okay, so that's why this is a negative part. That's why in this name, as you can see, at first they named potassium, then this complex ion part which is hexacyanidoferrate 3, right? So the next rule is, if the compound is non-ionic, it means there are some coordination compounds which are non-ionic, means neutral. The name of the compound is written as one word, means there will be no space, there will be a one word, that is the name of this neutral coordination compound is given without any space. Okay, now let's do some examples. In this case, this is cobalt. There are uh, two chlorine ligand, and there are four ammonia ligands, okay, inside this coordination sphere, and outside of this coordination sphere there are one chlorine ligand. Now into the polar solvent it will breaks into this, right, because chlorine is a anionic ligand, so it will produce Cl minus, so therefore there will be a plus one charge outside of this complex ion, right. So now in this case, this is the positive part and this is the anionic part, so we have to write the name of this positive part at first, which is tetraamine dichlorido cobalt 3, then there will be a space, then chloride. Now why there is a space? Because this is a rule, okay, we have to give a space between the coordination sphere and the ionization sphere, we have to give a space. As we can see here, they gave a space after potassium. Why? Because the potassium is in the ionization sphere, that's why they gave a space, then they write again, they write the name of this coordination sphere. Okay, so this is the rule. Now this is nickel tetracarbonyl, which is a neutral complex. So for this complex, as you can see, there is no space. Why? Because the neutral complex, there will be no space, the name will be as a one word. Okay, the name will be as a one word. So this is tetracarbonyl nickel 0, because it contains zero charge. Now in this case, we write here 3. How can we write this? After calculating the value of the metal charge. Okay, so which I already told you, how can we calculate the metal charge. So again we can do, we can do this, let's do it. So this is x plus, there are there are two chlorine ligands, so each of them contributes -1 charge, right. So there will be 2 into -1, right, plus it is a neutral ligand, so it will contribute 0 charge. So there are 4 ammonia into 0, again minus, there are 1 chlorine which is minus, which contributes -1, so there will be plus of -1, right. We can write it plus of -1 plus of -1 is equal to 0, because overall it is a neutral complex, right, means there are no charge out of this complex, right. This is a complex containing this chlorine ligand, there is no charge, so that's why we can write this. Now x minus 2 plus 0 minus 1 is equal to 0, or x minus a minus, it's plus, so -2 and -1 -3 is equal to 0, or x is equal to +3, right. So that's why we write 3 here, because cobalt contains 3 charge, +3 charge, that's why we can write 3 here. Okay, so this is the way we will calculate the charge of this metal, and we will write after the name of the metal. So now the name of the coordination sphere begins with the name of the ligands. Okay, now in this case, nickel tetracarbonyl, right. So this is a coordination sphere, they starts naming this coordination sphere with the name of this ligand, which is tetracarbonyl, right. So this is the rule. Again we can see, in case of K3 FeCN6, in the naming of coordination sphere FeCN6, they name first hexacyanido, then the name of the metal. In this uh, cobalt complex, they name the tetraamine dichlorido first, then the cobalt. So this is the rule. the name of the coordination sphere begins with the name of the ligands. Okay. Now the next rule is the number of the ligands is designated by the following prefixes. Now the number of the ligands, in this case there are 4 carbonyls, so the number is 4. So that's why they use this tetra prefix. Okay. In this case the number is 6. 6 cyanide ligands is there. That's why they use this hexa prefix. In this case there are 4 ammonia, that's why they use tetra, and 2 chlorine, that's why they use di. Okay, so there are some prefix uses in case of number of these ligands. So for 2 it's di, for 3 it's tri, for 4 tetra, 5 penta, 6 hexa, 7 hepta, 8 octa, 9 nona, 10 deca, 11 undeca, and 12 dodeca. So these all are the prefixes which use to designate the number of the ligands. Okay. Now the next rule is, if the name of the ligands already contain one of these prefixes, then their number is designated by. Now it means, for example, nickel, this trifluorophosphine, there are 4 trifluorophosphine and nickel, right? For this complex the name is tetrakis trifluorophosphine, then nickel 0. Now as you can see, this trifluorophosphine already contains this prefix tri, so we cannot use this tri prefix again. So for those ligands which already contains this tri, di, penta, hexa kind of prefix, we cannot designate their numbers by those prefixes. Okay, so we have to designate their numbers by, for 2 it bis, for 3 tris, for 4 is tetrakis, 5 pentakis, 6 hexakis, 7 heptakis, 8 octakis, and 9 enia. Okay, so these are the prefixes which uses for those kind of ligands which already contains this di, tri, tetra, penta kind of prefixes. Okay. Now the next rule is, if there are different types of ligand, these ligands are named in alphabetical order. Okay. For example, this cobalt complex, cobalt triammonia, there are 3 ammonia, 1 chlorine, 1 cyanide, and 1 NO2, right? For this complex, as you can see, there are different types of ligands are there. So in this case we will name the ligands in alphabetical order. It means this ammonia start with A, right? This is a chlorine start with C, cyanide also start with C, and nitro it start with N. So in alphabetical order, A comes first, then C, then N. So we will do in alphabetical order. We will do their names in alphabetical order. So the name is triamine because there are 3 ammonia. So triamine, then chlorido, 1 chlorine, that's why chlorido, then cyanido, then nitro. After that cobalt, then it's 3 because the charge of this cobalt is 3, that's why 3. Now this is not the correct way to write the IUPAC naming. Why? Because the name should be in a one sentence, sorry, in one word. Okay, so as you can see, this way I write up to here, then I break, and again I write here. This is not the correct way to write the IUPAC naming. The IUPAC naming should be in a one word. There should be no space and no break. Okay, there should be no space and no break. Okay, the name should be in a one word. So I will rewrite here. It is triamine chlorido, then cyanido. Again, okay, again I am there is no space, so I can write here, I cannot write here. So okay, I will do this example again after this whole video, okay, because I don't have space here, so I will do this name at last of this video, so please wait. I will do this name at last of this video. So these are some names of the ligands, and these are examples of the ligands and the names which use in the IUPAC naming, okay, which use in the IUPAC naming. For PPH3, PPH3 is named as triphenylphosphine. CO3 minus is carbonato. CH3NH2 is methylamine. SO2 sulfoxide. N3 minus is nitrido. Nitrido. For N3 minus is azido. Okay, so these and these are different. In this case, there is a 3 minus charge on one nitrogen, and there are 3 nitrogen atoms contain 1 minus charge, which is azido. Okay, which is azide but named as a azido in IUPAC nomenclature. For SO4 minus 2, it is sulfato. S minus 2, sulfido. NO3 minus, nitrato. CH3 whole 2 N minus, dimethylamide. CH3O minus, methoxo. C2H5O minus, ethoxo. CH3 methyl. C2H5 ethyl. C2H C6H5 phenyl. C3H7 propyl. So these are some examples of the ligands and their names. In the previous video, I already gave you so many other ligands and their names and with their structures. So if you have not watched that video, please go and watch it so that you will get understand the names of the so many other ligands. Okay, now the next rule is when the coordination sphere, sometimes it is complex ion, is negatively charged, the name of the metal is altered to the end in it. Okay, like for previous example is K3Fe3N6, where this Fe3N6 is a negatively charged complex ion, right? So that's why the name of this iron is named as a ferrate. Okay, ferrate. There is a 8 in the end of this name of this metal. Why? Because this is a negatively charged coordination sphere or complex ion, right? So this is the rule. In case of negatively charged complex ion or coordination sphere, the name of the metal is altered to end in ate. For scandium, it is scandate. For manganese, it is manganate. For cobalt, it is cobaltate. For nickel, it is nickelate. For platinum, it is platinate. For iron, it is ferrate. Okay? For iron, it is ferrate. For silver, it is argentate. For gold, it is aurate. Sorry, it is aurate. Okay, so it is aurate, aurate, aurate. For zinc, it is zincate. Okay, so these are the some examples of the metals and their name when their complex ion is negatively charged. Okay, is negatively charged, then their name will be altered into the end with 8. Okay, as you can see in the previous examples also. Now there's a next rule is for positively charged or for neutral complexes, the name of the metal is unaltered. It means, like for this example, nickel tetracarbonyl. So this is a neutral complex. There is a no charge outside of this complex. That's why the name of the nickel is written as a nickel. Okay, there is no 8 at the end. For this complex, this is also a positively charged complex ion. Okay, it contains a positively charged complex ion. If we break it, then we will understand. Okay, as you can see, this is +1. Okay, this is Cl minus, right? As you can see, this is Cl minus this is plus 1. So it is a positively charged complex ion complex, right? This is a positively charged complex ion, so that's why their name of this metal is normal, that is cobalt, no 8 at the end, right? So these are some rules of the IUPAC naming. So this is the way we can write. Now let's do that example, this cobalt triammonia example. Okay, triammonia, then Cl, then cyanide, then NO2. So this is the complex. So we should write the name of this complex like this way: triamine, now chlorido, then cyanido, right? So cyanido, no space or no break. Okay, then cyanido, then nitro, cobalt 3, right? So this is the name of this complex. Okay, so I told you I will do this example at the last of this video. So this is the example. So these are the all rules of IUPAC nomenclature, and also the how to calculate the metal charge of coordination compound. Okay, so I hope you like it. In the next video I will do some examples of IUPAC nomenclature, and after that video I will talk about isomerism of coordination compound. Okay, so please like, share and subscribe. Thank you so much.